This video is about human influences on evolution. So, we will be having a quick chapter summary and after that, an introduction into this topic human influences over human evolution, increase in longevity and natural selection, genetic birth defects, later, some topics related to maintenance of deleterious alleles, later, about eugenics in detail, some aspects of reproductive technology, gene therapy, then the rise of agriculture, domestication, then genetic engineering of food crops and animals, some major points related to GM technology, and some concerns about GM technology, our influence on the evolution of other species and their environments, and which are the key terms involved in this topic. So let's start learning about this topic. Any attempt to influence our own evolution has to confront the potential incompatibility of cultural and phenotypic fitness. For example, social and medical advances maintain alleles in particular groups or in our species as a whole that would be deleterious in other organisms. We discuss two approaches to influence our own evolution: eugenics and gene therapy, as well as human efforts to engineer the genomes of other species, all of which raise ethical concerns. Movements to influence evolution through selective breeding or eugenics arose as one aspect of the application of Darwinian principles to societies like social Darwinism. Although often not recognized as much, eugenics continued to be practical by individuals in their use of assisted reproductive technologies, assisted methods of reproduction. Humans have been engineering the gene pool of other organisms since the origins of agriculture and the domestication of plants and animals. Today, genetically modified organisms, GMOs in short, are commonplace. So, prevailing is human influence that when humans are present, altered evolution of other organisms is not the exception but the expectation. Longer human lifespans are generally thought desirable, but in fact, natural selection rarely influences the features of post reproductive individuals, including features associated with longevity. Given the large size of human population and the limits on resources, lowering fertility might be advantageous, but biologically high fertility has selective value. A large proportion of the human population is or will be affected by alleles that persist because of forces that maintain genetic variation or because the intervention of modern medicine allows individuals with what might otherwise be deleterious alleles to live longer and reproduce. These are the topics of the first and second parts of this chapter. So, human influences over human evolution. Humans now have the technology to change themselves and the world in which they live. Although cultural considerations can transcend many biological constraints, improvements in human lifestyles bring us face to face with biological limitations. Our biological heritage stresses early reproductive success, after which physical deterioration sets in, increased life expectancy, reproduction into decades beyond our 30s, and our ability to contribute to society into our 70s and 80s all stand in stark contrast to this biological heritage. Human cultural development requires continued plasticity, adaptability, and longevity, but also is limited by biological decline as we age. Increase in longevity and natural selection. In most organisms that attain reproductive maturity relatively early in their potential lifespan, survival after reproducing tends to be short lived or non existent. In contrast, individuals in many modern human societies enjoy a long period of post reproductive longevity. Early in our own evolution, only about half the human population passed the age of 20, and not more than 1 in 10 lived beyond 40. Life expectancy remained between 20 and 30 years until the Middle Ages, like 5th to 15th century, then rose somewhat beginning with the Renaissance period in Europe. Life expectancy has risen sharply among Europeans, Americans, Japanese, and some others in the last century and a half, from about 40 years in 1850 to the present high 70s or low 80s. Less developed countries also have seen dramatic increase, the major exception being those countries in Africa where the AIDS and epidemic, poverty, and war have reduced already low life expectancy to as little as low 30s. These changes in longevity are important. They indicate that as a result of improvements in sanitation, diet, and medical practices in developed countries over the last century and a half, natural selection on individuals in those societies has been influence in fitness. That is, on the number of offspring produced, which more and more is a matter of personal choice. Further, many of the ills resulting from our changed lives, diabetes, heart diseases, and cancer, affect us mostly in our later post reproductive years. Consequently, there is little or no chance for natural selection to weed out susceptibility to these ills. In biological terms, an individual who has produced three children and at the age of 50 develops cancer or other disease with genetic components is no less reproductively successful than an individual of the same age who has produced three children but does not suffer from such diseases. Our increasing longevity has had an even more dramatic impact on global population with major implications for humanity and for world as a whole. This discussion of longevity, however, should not leave you with the impression that humans are no longer subject to natural selection. Natural selection can readily be detected in populations in which technological change has been slow. Humans continue to adapt to changing environments, and those changes can be measured in rates of genetic change. In a study that looks at rates of genetic changes in the historical context of migration out of Africa, documented that even 7% or more of the human genome has changed over the past 40,000 years, and that the advent of agriculture correlates with the hundredfold increase in the rate of changes in the human genome. The Tibetan Plateau lies at an average elevation of about 4,600 meters above sea level. Settlement of this plateau by human several thousand years ago required adaptations to the low levels of oxygen at such altitude. The partial pressure of O2 at sea level is 13.3 kilopascal. At 4,300 meter, it is 4.7 kilopascal. Most people can cope with oxygen levels found up to around 2,500 meters, at which the partial pressure of O2 is 8.2 kilopascal. But at higher altitudes, humans can succumb to altitude sickness and inability to cope with extremely low oxygen levels at high elevations. Tibetans living on the plateau have adapted to these low oxygen levels. Part of that adaptation involves the widespread presence of two genes that are found only rarely in other populations, consistent with positive selection for the genes in humans living in high altitudes. One gene, EGLN1, EGL9 homology 1C elegans, produce a protein involved in the formation of hypoxia inducible factor alpha proteins, transcriptional complexes, and major sensors of oxygen levels in cells that influence hemoglobin levels. The second gene, PAR alpha, peroxisome proliferator activated receptor alpha, produces a nuclear receptor involved in the oxidation of fatty acids and energy metabolism, both of which are enhanced in Tibetans. Next, genetic birth defects. Despite improvements in medical care, alleles persist in human populations that in other organisms would be classified as deleterious because of their negative effects on adaptiveness to the environment or on fitness. Here, we discuss how such alleles are maintained in human populations. The number of children born with marked physical or mental abnormalities is conservatively estimated at about 20 to 25 in every 1,000 births in the United States. The mortality rate ascribed to congenital malformations account for about 15% of all infant deaths. Other abnormalities not immediately noted at birth may become apparent during childhood years, such as defects are more common than usually realized. In various studies, about 30% or more of hospital admissions of children and 50% of all children deaths are ascribed to birth defects or to complications consequent to such defects. Although not all birth defects are genetic, the proportions of those that are is high. The incidence of each individual genetic disorder is low. Cystic fibrosis is 0.05% of live births. Tay-Sachs disease is 0.001%. Trisomy 21 is 0.13%, and congenital heart defect 0.4%. Summing the incidence of genetic disorders in humans, whether autosomal, X-linked, or chromosomal, gives a total frequency of around 2.6% of live births. If genetic defects such as muscular dystrophy that appear later in life are included, the frequency doubles to around 6%. If, in addition, we conclude less obvious conditions that nevertheless have strong genetic components, impaired resistance to stress and infection, defects of harmful genes touch a significant proportion of the human population. Maintenance of deleterious alleles. Phenotypically, normal human offspring carry a genetic load of 1 to 8 deleterious lethal alleles. 1 to 8 deleterious lethal alleles, which, if homozygous, would result in early death. Two important questions arise: what accounts for the prevalence of these harmful alleles? What, if anything, can be done to rid ourselves of them? The reasons for the high frequencies of deleterious alleles are not fully agreed upon, although there is little question what they originally arose through mutation. In one hypothesis held by the late scientists and others, such alleles may offer considerable advantage to their heterozygous carriers by producing some form of hybrid vigor. According to this hypothesis, a gene will be maintained in the population even if the homozygote is relatively inferior in fitness. Another school, formerly headed by the late American geneticist Herman Miller, was based on the hypothesis that such genes produce no advantage of any kind. Their frequency is high because the usual effect of natural selection has been artificially reduced. According to Muller, genotypes that were defective and would be eliminated in earlier times are now retained in the population by medical techniques that enable these alleles to be passed on to offsprings. If not eliminated by skeleton, the selection pressures themselves change over time. Deleterious alleles will eventually increase in frequency in accordance with their mutation rates. Because mutation rates are usually low, the frequency of any particular allele will increase rather slowly, but as there are many possible deleterious alleles, the allelic load will increase sufficiently. So, nearsightedness is a trait whose frequency has been likely increased in recent periods but can be correlated quite simply by wearing glasses. Corrected quite simply. Nevertheless, and despite or because of advanced medical care, a great many alleles that would affect fitness in other organisms are retained in human population. Next is about eugenics. In his dialogue, The Republic, Plato suggested that humans could be improved through selective breeding. In his ideal philosopher's state, only the most physically and mentally fit individuals will reproduce. Their offspring would be raised by the state, and the governing class would be selected only from the most superior. In this 19th century form, suggestions for improving the human gene pool come under the name eugenics, a term coined by Francis Galton in 1883. From the Greek word eu means good and gen means birth. Good birth. So Galton was fascinated by the inheritance of mental ability. His first book, Hereditary Genius, published in 1869, was an in-depth and statistical analysis of the inheritance of mental ability in the British upper class. Galton introduced the bell curve in his statistical analysis, coined the phrase nature versus nurture, and wrote the first book on eugenics. From 1865 on, Galton promoted the idea that the evolution of human traits through natural selection could be substituted by their evolution through selective breeding. What nature does blindly, slowly, and ruthlessly, man may do providently, quickly, and kindly. As it lies within his power, so it becomes his duty to work in that direction. Coming from a brilliant family himself, Galton was impressed by the way in which intellectual and personality traits tend to run in families. Convinced that such traits will inherited, and drawing on his knowledge of animal breeding, Galton concluded that judicious marriage over several generations could produce a highly gifted race of men, and thus taught the reversion to mediocrity. He believed to be threatening society as a result of excessive breeding by those who are not superior. Galton's ideas were taken up and developed by many prominent thinkers, like social Darwinists. Early eugenics reflected their personal and cultural biases in which traits they deemed undesirable. So strong racist and class-minded biases played a part from the beginning. Charles B. Davenport in 1866 to 1944, an influential leader of the early 20th century eugenics movement in the United States, exemplified this racist approach by using New Englanders as the standard of comparison for our American social groups, irrespective of their country or origin. According to Davenport and other members of his eugenics record office, which from 1910 to 1944 collected an enormous database of information about American families. Particular groups could be characterized by social traits with identifiable hereditary components, Italian violence and Jewish mercantilism being two examples used. No evidence supports the biological superiority of any particular human group in respect to their social characteristics or intelligence. Many characteristics considered desirable, high intelligence like aesthetic sensitivity, longevity, and good physical health, are not associated with single genes that are easily identified, but by complexes of many genes acting together and responding to different environments. As learned from domesticating animals, selective breeding to develop beneficial gene complexes is difficult. So, selective breeding involves complicated schemes based on selection of parents and testing of progeny under controlled environmental conditions. Selective breeding enhances the preferred characters, but at the expense of the deterioration of other characters. Eugenics believed in active intervention in breeding. Two avenues of action were promoted and in some instances followed: positive eugenics, which aimed to increase the frequency of beneficial genes, and negative eugenics, which aimed to decrease the frequency of harmful genes. Francis Galton's approach of encouraging particular people to marry is an example of positive eugenics. Singapore's campaign in the 1990s, in which young graduates were offered inducements to produce children, is another. Unfortunately, however, negative policies dominated the vast majority of government programs instituted roughly from the 1890s to the 1940s. So strong has the influence of the eugenics movement that almost every non-Catholic Western country was affected. Other areas, including the southernmost Latin American states, where policies favored whiter complexions, and since the early 1990s, China, viewed today through the prisms of human rights, we are appealed to the legislation, one of its draconian and enacted and enforced in the name of eugenics. Methods employed include restrictions on immigrating and marriage, racial segregation, including bans in the United States on marriage between whites and African Americans, and overturned by the Supreme Court only in the 1967. Compulsory sterilization of the feeble-minded certain criminals and others deemed unfit, forced abortions. In Germany under the Nazis, genocide of these, especially Jews, regarded as racially inferior and thus a threat to the purity of Aryan race. In the United States, home to the second largest eugenics movement after Germany, marriage prohibitions were enacted in many states during the early decades of the 20th century, and tens of thousands of individuals were sterilized, and last of them in the early 1960s. Backing the eugenics movement was a large body of research. Fortunately, even from the early years, some scientists and members of the general public were sharply critical for the methods employed and the conclusions drawn from these findings. Later, modifications of human reproduction continues in a quite a different type, like modern reproductive technology, which is the next topic we are going to learn about. So, reproductive technology, the search for healthy children by today's parents has many eugenics overtones, genetic counseling before consumption, artificial insemination, testing the fetus for inherited disorders, selective abortion of fetus deemed defective, ultrasound examination, and in vitro fertilization, including pre implantation screening of embryos, are all in effect eugenic practices, albeit voluntary and on an individual basis. So, eugenic practice and reproductive technologies both change gene frequencies in populations. In countries where reproductive technologies are widely used, the incidence of some congenital disorders has declined sharply in recent years. In Taiwan, for instance, the incidence of thalassemia against newborn dropped from 5.6 to 1.21 per 100,000 over 8 years. Because prenatal testing is expensive and often invasive, ultrasound is the only technique carried out as a matter of routine. Other tests are usually performed only when the family history or mother's age, in case of Down syndrome, indicates a clear risk that a particular mutation or chromosomal abnormality could be present. So, armed with knowledge gained from sequencing the human genome, it may not be long before screening tools can be designed to test for all known disease causing mutations. Given the beneficial cost and risk to the fetus of prenatal screening, however, the most likely use of such tools will be in pre implantation testing of embryos conceived in vitro fertilization. Via in vitro fertilization, reproductive technologies, including genetic screening, evoke a host of ethical and social concerns, including what constitutes a disease? How do potential parents make an informed choice among the options? Who has the right to know about an individual's genetic makeup? Schools, employees, insurance companies, government? Who owns this information? Despite the many ethical concerns, it is likely that the use of modern reproductive methods will continue to increase and that over time they will have a larger and larger impact on our genetic pool, at least in the wealthy countries and populations. For now, however, and into the future, a far greater influence is likely to be modern medicine in general. Before open heart surgery, few, if any, individuals with severe congenital heart disease survived childhood, less benignly despite laws banning the practice. The widespread use in India and China of ultrasound followed by abortions to ensure the birth of the male child is leading to significant imbalances in the male female ratio of these societies. So the argument could be made that because only a handful of children now die of infectious diseases in countries with robust healthcare systems and door to population with weaker average immune systems is being opened. Door to population with weaker average immune system is being opened. Next, gene therapy. An era of research evoking great interest in gene therapy, the introduction of genetic material to treat or cure a medical condition. Human traits, which begin trials in which began in 1990s, have targeted several diseases using a variety of methods and vectors. Despite hundreds of trials, a great many problems remain. In 1999, an individual in an American gene therapy trial died, most likely as a result of a severe immune response to the viral vector. A further major setback occurred in French trials carried out on young children with X-linked severe combined immunodeficiency or SCID disease, also known as a bubble boy syndrome. Although 9 of the 10 children in this trial were successfully treated, 3 subsequently developed cancer, T-cell leukemia in particular, in a study conducted in 2006. One-third of mice administered in the same gene as was used in the X-skid trial developed lymphoma later in life. As of this writing, no therapy product had been approved for sale in the United States. In May 2007, biologists corporations like Syngene was approved by the United States Federal Drug Administration for consideration of phase 1 clinical trials as an orphan drug to treat pancreatic cancer. In 2011, the phase 1 and 2 clinical trials complete. Rexin G remains the first and the only targeted gene delivery system designed to treat metastatic cancer. Which one? Rexin G. The rise of agriculture. The transformation of human societies produced by cultural changes over the past 10,000 years has been dramatic. This is readily seen in the origin of evolution of agriculture. The evolution of agriculture is not limited to human societies. However, cultivation of land, crops, or families of other species, agriculture has evolved independently in four groups of animals: humans, termites, bark beetles, and ants. Ant agriculture arose when a lineage of ants began to cultivate a range of species of fungi some 50 million years ago. Three novel systems of ant fungal gardening evolved in the last 30 MY by involving the cultivation of separate species of fungus. A further system, cultivation of a single species of fungus by leaf cutter ants, that evolved 8 to 12 MYA, is now the dominant form of ant agriculture in the New World tropics. Somewhere during the Neolithic age, the long prevailing hominin lifestyle of hunting, gathering, fishing began to give way to the cultivation of food using domesticated plants and animals. Energies formerly expanded in finding food were directed into methods of agriculture. Eugenic energies formerly expanded in finding food were directed into methods of agriculture. Although originally developed in the Middle East, China, and Central Africa, such changes spread rapidly. Within 1,000 years or so, some form of agriculture had begun in many contiguous areas. Within 5,000 years, agriculture and the technologies are estimated extended widely. The most immediate and most far-reaching effect of agriculture was to increase food supply many-fold, a change permitting larger populations and a greater population density in agricultural communities. What matters here is the change in human lifestyle, although there are uncertainties concerning whether sedentary communities proceed or followed agriculture, and whether agriculture was stimulated by climatic changes or by increased Neolithic social complexities, and did not take any generations for humans to settle arable areas on a permanent basis. Next topic of domestication and genetic engineering of food crops and animals, along with concerns about GM technology, influence on other animal evolution will be dealt with the help of next video.